do an example of how I would facilitate the cash register activity when introducing binary numbers. So I usually start with giving kids actual paper tokens, so paper coins. We have a ones coin, a twos coin, a 4-unit coin, and an 8-unit coin. And so I'll tell them, okay, I have a store, and I am selling things at different prices. And nothing in my store is free, so everything costs at least 1 cent. So the question is, what are all of the prices of the things in my store that you can't buy with the coins that you have? And let's just say I don't give change. So it's exact change only. And if you have the coins, you can buy it. Now, the most expensive thing that we can buy, and I'll ask them, how do you figure that out? Well, it's 8 plus 4 plus 2 plus 1. So that's 15. So we'll say right off the bat that the cheapest thing you can buy is 1 cent. The most expensive thing is 15 cents. So which things can't we buy? And students will think about that for a while, and then they'll say, well, what do you mean sometimes? And I'll say, okay, well, certain things that you can't buy, like 11. If something's 11 cents, you don't have exact change. You can't buy something that's 11 cents. There's an example. And then the students will say, well, no, you can. You can buy something that's 11 cents. You use the 8 and the 2 and the 1. Oh, you're right. I guess you can buy, okay, so that's a bad example. But 13 cents, for example, that's a better example. You can't buy anything that's 13 cents. Well, hold on, wait a second. No, hold on, you can go 8, 4, 1. Oh, you're right, that does add up to 13. Huh, okay. And then at this point, students will start to say, well, you can make every number. And I'll say, well, is that true? Does everybody believe that? Can anyone find an example of something that you can't make between 1 and 15? Can anyone find any value? And if you give them a few minutes, and then they'll say, well, no, you can make every value between 1 and 15 with the coins that you have. Because you could use just the 1, you could use the 2, you could use the 2 and the 1 to make 3, you could use the 4, et cetera, et cetera. So once we have some general agreement that you can make every number from 1 to 15, then the second question I ask is there more than one way to make any of those numbers? And students will figure out that there is only one way to make every number from 1 to 15 if you have these coins. And, I ask for a show of hands. And once we kind of have all agreed and proven to ourselves that both those things are true, you can make every number from 1 to 15, and every number you can only make in one and only way. 1 and 1 only one way. Then we go on to the next one, right? So we'll say, okay, let's imagine what would be the next coin. Well, logically, the next coin after the 8 would be the 16, because the pattern here is they double each time. And sometimes I'll go and say, okay, well, what's the next one after that? It'll be 32. But if we do that, then we say, okay, well, now what's the new maximum? Let's say we add a 16 and a 32 to the 8, the 4, the 2, and the 1. What is the new maximum? Well, with this one, it's 31. 16 plus 15 is 31. If we add a 32 coin, now the new maximum is 63. And so let's see if those same two rules hold true. Can we still make every number from 1 through 63 in one and only one way? And so to prove that to ourselves, we can pick some random things. Like, let's say we wanted to make 37. Well, you'd use the 32, and I guess you use the 4, so that's 36, and then you'd use the 1, so that's 37. And what if you wanted to make something like 53? So 53, we'd probably want to use the 32 coin, the 16, so that's 48. That gets us almost there. This would give us 52, and then one more would give us 53. So I let kids play around with this for a few minutes just to practice making the different things line up, right? Making the different values. And then I'll say, well, let's go ahead and organize these. So go ahead and draw a line across your paper and create sort of trays. We'll make this like a cash register. And let's line them up in this order, smallest to largest, above the line. And let's say that if we're not using it, if we're leaving it in the drawer, we're not gonna drag it below the line. But if we do decide we're gonna use a coin, we can drag these down. So let's all make 27. 27 is gonna be 16 and 8, so that's 24. And then a 2, so that's 26, and then a 1, so there's 27. So 16, 8, 2, and 1, 27. That's great. Let's make 49. So 49, we would want to do 32 and 16, so that's 48, and a 1, so it's 49. So that's helpful. And once students get in the habit of moving it either below the line to use it or moving it back up above the line if we're not going to use it, then we just go ahead and we label it. We say if we're using it, these are the coins we're using. And if we're not using it, we leave it above the line. What does this add up to? This is 22, right? 16 plus 4 plus 2. Another way to say don't use and use is we might say no, because we're not using them, and yes, we are using it. Or since we're dealing with computers, instead of saying don't use and use or no and yes, why don't we just use 0 and 1? And so if we label these as 0 and 1, well, which ones are down in the bottom category? If we drag these down, then what we can do is we can represent what we've used simply with zeros and ones, right? So a 1 means we're using it, a 0 means we're not using it, and we're using the 8, and we're using the 4, and we're using the 1. So when you add all of these together, you end up with not 53, but in fact 45. And so we've got 32, 8, 4, and 1. And in binary, that's 101, 101. And that's essentially how you use ones and zeros to keep track of essentially place values. Because, of course, the reason we're going from 1 all the way up to 2, 4, 8, 16, 32, and then ultimately 64 and 128, these are actually powers of 2. So 2 to the 0th power is 1. 2 to the first power is 2. 2 to the second power is 4, and so on and so forth. And each of these we can refer to as a bit. A bit stands for binary digit, and it is the smallest unit of digital information. So essentially 0 and 1. And if you use all your coins, essentially, it would be 1111, 1111. That is the highest possible value that you can represent with 8 bits, and it's 255. Another way to say 8 bits is 1 byte. 8 bits is 1 byte of information. But I find that this model is a nice way to keep it in your head about how to actually make different numbers. So for instance, I would say at this point, let's just go back to our 6 bits, 32, 16, 8, 4, 2, and a 1's coin, and let's figure out what does each of these binary numbers represent. And students can actually use the coins to kind of figure this out, or eventually they can start to figure it out in their head. And this ultimately is the set of answers for these problems. And students should be able to go the other way too. So if we wanted to make 55, for example, we would pull down the 32, the 16, the 8, and the 1. So how would you actually, and then 111001. So it's good to use this model to introduce binary and ultimately give kids enough practice so that they can go back and forth. So that's the binary cash register activity.